Hello, today we will talk about orthogonal trajectories. So this is actually one of the applications of first order and first degree differential equations. Okay, so let us just go ahead with it. Suppose you have a family of curves. When I say a family, it means that there are many curves. Okay, for example, all right, let us take an easy example. Suppose these are the curves. Okay, circles where the origin is the center. All right, you are having so many circles, that is, it is a family of curves or family of circles in this case. Okay, this continues. Okay, it continues forever, and we are having this family of circles. I want to find another system of curves or lines which is perpendicular to each and every circle. Okay, you notice that this line, it is perpendicular to this first circle. This line is also perpendicular to the second circle. It is also perpendicular to the third circle. Okay, so this one, it is perpendicular to each and every member of the family. Similarly, this line, it's also perpendicular to each and every member of the family. Okay, if you remember, radius is perpendicular to tangent. So if we draw even other lines in this way, or even you can draw it in this way, all right, so many of them that passes through the center, what you can say is that each line is perpendicular to each member of the family. Okay, so in this case, we will say that these lines, okay, they are the orthogonal trajectories of the circles. Again, I repeat, these lines, they are the orthogonal trajectories of these circles. So that is what we can say. Now let us now define. I think with that example, it has become a bit clearer of what we are going to do. So I will define in this way. Orthogonal trajectories. Let there be a family of curves okay, let us say that this family is represented by C1. Okay, suppose there is another family of curves C2 such that each member of C2 is perpendicular to each member of C1. To each member of C1, then C2 is said to be an orthogonal. Okay, maybe I should be more specific. Then each member of C2 is said to be an orthogonal trajectory of C1. All right, so if we have to draw this one, we can imagine a very general case, which is, let there be a family of curves C1. Okay, suppose the family of curves C1 are in this way. Okay, they can go in any way, in any direction that you like. Okay, if we have to find the orthogonal trajectories, then each member of another family, okay, which I will maybe depict by blue. Okay, so this black one, it is the curve C1. Okay, I will depict by blue color the orthogonal trajectories. So we have to draw in such a way that it is perpendicular, okay, to this curve C1. Okay, so we will have to draw in this way. All right, again, it has to be perpendicular to this. So if it continues, then maybe like that. Similarly, over here, okay, it has to be perpendicular to this. Okay, again, it has to be perpendicular to this other curve right here. And again, it has to be perpendicular to the other curve. Again, it has to be perpendicular to this one. Okay, if we continue, then we have to draw in such a way. You notice that at each and every point, okay, we are not exactly having lines. Okay, what I mean to say is that these blue curves, okay, they may not be straight. Okay, as in the previous example when we were having straight lines that are orthogonal trajectories of the circles. So now comes the question, how exactly do we determine orthogonal trajectories? And because over here we are dealing with curves, okay, what do you mean when we say that it is perpendicular, that one curve is perpendicular to another? Just as we are saying over here, this blue line is perpendicular to the black curve. Okay, so you must remember something. Over here we will use something that is very important, that we will use tangents and normals to know when a curve is perpendicular to another curve. For example, okay, I will draw another way. Okay, I will zoom it. Let's see. Okay, so let us take a look at just a simple case, okay, where we are having only one curve. Let us say that this one, okay, suppose we are concentrating on this point. Okay, suppose we are concentrating on this point. Then if we have to know the angles between the two curves, and if suppose this blue line that is passing through this one, okay, it can also be curve. It is perpendicular to this black curve. The blue curve is perpendicular to the black curve. Then we will have to use normal and tangents. You must notice something over here, is that if we draw the tangent for this black curve, then it will be like this. If we draw the tangent for the blue curve, it will be something like this. Okay, so if the tangents of the curves of the black and the blue one, they are perpendicular, then we will say that the black curve is perpendicular to the blue curve. I will write it down. If the tangent okay of the blue curve at P is perpendicular to the tangent of the black curve at P, then we say that the two curves are perpendicular. Okay, so over here I am using color codes black and blue. You can easily replace this one. If the tangent of the first curve at P is perpendicular to the tangent of the second curve at P, then we say that the two curves are perpendicular at P. Okay, I should even mention that point. Okay, but also you notice something. Okay, so this one is the tangent of first curve. And this one, it is the tangent of second curve. You notice something over here, that the tangent of the second curve is nothing but the normal of the first curve. Okay, so that is what I say, that we will have to use tangents and normals. So notice that the tangent of second curve is the normal of first curve. Okay, if the two curves are perpendicular at P. So this is what I am saying. And because we are using tangents and normals, okay, now from curves we have gone into straight lines. Given curves, now we are using tangents. Tangents are just straight lines. So how exactly do you determine that two lines are perpendicular? That is when we use the slopes. Okay, so another point that we should note over here is that to determine that two lines are perpendicular, we can use the slopes. Okay, so for this we have number one, the slope of the tangent of the first curve. Okay, if you remember, it's given by dy dx. Okay, what will be the slope of normal at the point P? Okay, slope of normal of first curve, it is given by minus dx dy at the point P. Okay, and because the tangent of the second curve is the normal of the first curve, so we can also say that the slope of the tangent, okay, the slope of tangent of second curve, it is in fact equal to the slope of the normal of the first curve at P, which is equal to minus dx dy. Okay, if m1 is the slope of the first line and m2 is the slope of the second line, if the first line is perpendicular to the first line, okay, if the two lines are perpendicular, then we will get minus 1. The slopes, the product of the slopes will be minus 1. So that is exactly what we are having over here. You can think of this one as multiplying. Multiply the slope, multiply the other one, okay, you will get minus 1. Okay, I hope you can see that. Okay, so with that being said, we are now set to, okay, to find the orthogonal trajectories of curves. Okay, how to find the orthogonal trajectories? Okay, number one, suppose we have suppose the equation of the given family is f x y a is equal to 0. Do not worry, I will explain an example why it should be f x y a equal to 0. Number two, first we obtain the differential equation of the family. Okay, so because it is a differential equation, it will also involve f, it will involve x, it will involve y, and then it will involve another term which is dy dx. Okay, and there will still be a constant a, this parameter a. Okay, but first we will also have to eliminate. First we obtain the differential equation a equal to 0. Number 3, we eliminate a from 2 by using 1. Okay, after eliminating, we replace dy dx, replace the slope of the first curve by the slope of the second curve, which is minus dx dy. Okay, after this is done, okay, then we solve it as a differential equation. All right, then solve the differential equation. Number 5, solve it. Okay, so let's see. All right, I will give a very easy example first. Okay, let us see. Do remember the steps, it's very important. Okay, so exercise. The first one will be find the orthogonal trajectories of the family x squared plus y squared equal to a squared. Okay, so if you notice this one, it is actually the equation of a circle. The radius is a. Okay, a is a parameter. So if you draw this one, okay, we don't need to draw it, okay, but just for you to understand, the origin over here is at 0, 0, and the radius is a. All right, the radius is a. So if we draw the circle, it will be something like this. Okay, but what happens here, we are saying that a is a parameter. All right, it is a parameter. That is, we don't know what the value of a is. It doesn't have a specific value. It can range. Okay, it can vary. So that is why even if the radius is a, which is another value, then we will be having another circle. Okay, so this is what we are having. Okay, so for all the values of a that we can think of, we will be having different circles, even smaller ones. Okay, so solution. That is why I'm writing this one as fxy a equal to 0. Remember the first step. Okay, we can write this one as x squared minus y squared a squared equal to 0, which is of the form f, x, y, and a. It is a function of x, it is a function of y, and it is a function of a as well, equal to 0. Okay, we can write it in this way, or we can just leave it as it is, no problem, but I hope you understand. Okay, or we can just leave it as it is, equal a squared. Okay, it's the given family. Okay, one thing to note down is that given a family of curves, we can easily write it in the form fxya equal to 0. Next, what we will do, differentiate. Okay, differentiate it to obtain the differential equation. Differentiating with respect to x. So if you differentiate this one, you will be getting 2x. Differentiate this one, you will get 2y dy dx. Differentiate a squared, it will become 0. Okay, so we will be having this. Okay, so remember that the second step is that we have to obtain the differential equation, which is a function of x. Okay, the differential equation, it will be a function of x, just like we are having here, a function of y, just like we are having here. Okay, an expression containing dy dx, which is over here, and also it contains a. Okay, but over here it does not contain a, no problem. Okay, let it contain, let it not contain a, no problem. So if it contains a, we have to eliminate it, but over here, since it does not contain a, we can skip step 3, okay, which is eliminate a in equation 2 by using 1, but over here we don't have a, so that's why we will leave it as it is. Okay, so remember that we were having circles. Next, what will we do? Now we can go to step 4, replace. So step 3 over here, it's not required. Replace dy dx by minus dx dy. So over here we'll be having x. Over here, okay, minus y dx dy. Okay, dy dx has been replaced by minus dx dy. So this is what we are having. Okay, next, what will we do? So this one, if you notice, it is a differential equation. So now we just need to solve it. All right, how do we solve it? We can just separate the variables. Okay, maybe let us write it down in this way so that it becomes clearer. Or we can write this one in this way. Remember that dy has to be on top. Dy upon y equal dx upon x. Integrated. So we'll be having log y equal log x plus log c, since everything is log. Okay, so I'm putting it in this way. So y is equal to cx. Okay, how exactly did I get this? Maybe I should write another line. Okay, properties of logarithm, log a plus log b, log ab. Okay, which is the required orthogonal trajectories. Okay, so let us see what exactly did we do here. Let us see. All right, so we were having circles. Okay, x squared plus y squared equal a squared. After doing all those steps, we are having the equation y equal cx. So this one, it is a family of circles. This one, it is a family of straight lines passing through the origin, y equal mx. Okay, so that is exactly what I say in the very beginning when I give you that example, that the orthogonal trajectories of the family of circles is just the family of straight lines passing through the origin. Okay, so I hope that is clear. Okay, just in case it is not clear about the method of how to do it, let me show another example. Okay, example number 2. Again, the same question, obtain the orthogonal trajectories, but over here it's y squared equal 4ax. Okay, so let's see. Okay, so the given equation, write it as 1. Okay, I won't even draw it, but just for you to know, this is an equation of a family of parabolas. Okay, differentiating with respect to x, we will be having 2y dy dx equal 4a. Okay, so this one is equation 2. Now, the difference between this question and the last question was that in the last question, there was no term a, but over here there is indeed this a. So what will we do? We will have to eliminate a from equation 2 by using 1. Okay, so what can I do? 4a from equation 1, we can write 4a equal y squared upon x. Okay, so that is why we can substitute here. Okay, so now we are having this equation 3. Okay, in step 3, after doing step 3, replace dy dx by minus dx dy. Okay, so what can we have? Okay, replace, we will be having, okay, 2y will stay as it is, dy dx by minus dx dy is equal to y squared upon x. Again, we can separate the variables and integrate. Okay, so over here minus 2, y and this y will get cancelled, so I will just write dx upon dy equal y upon x minus 2 dx equal y dy, and then we can integrate minus 2, over here will be 2x. Okay, 2x, x squared upon 2, y squared upon 2 plus c. So we can simplify. Okay, we will be getting minus x squared minus y squared upon 2 equal c. Okay, or we can simplify further. Okay, remember that C is a constant, so we can multiply by this constant. It will still remain as a constant, which we will denote by C1 multiplied by 2 throughout. Or we can even do better, again multiply by minus. Okay, we will be having this one equal C2, okay, which is the required orthogonal trajectories. So I hope that is clear about orthogonal trajectories. I will be sending some exercises in the WhatsApp group as well. So until then, okay, take care.